Greetings, students. This is allLogarithmsEqual, with another production. I decided to make a video purely dedicated to a very interesting function, y equals x squared minus 1. You may be surprised to know how much there is to say about this one, and for all I know, this might be the start of a new series on different unique functions. At any rate, please stay tuned for many interesting ideas and concepts behind this one simple function, y equals x squared minus 1. So the first thing I'd like to discuss is the geometric appearance of this function. And this one is rather obvious to anyone who has taken an elementary algebra class, but just to see a sketch of this function, it's worth noting that the function is a case of the conic section where its eccentricity is equal to 1, so it is a parabola. Now we know that for a parabola, the distance from its focal point is equal to the distance to a directrix, or a line on the other side of the curve. So in this case we have one focus, or focal point, at 0, negative 3/4, and the directrix right at about negative 5/4, I'm fairly sure. And in some sense, that is what generates this parabola. And by one definition, this means that the eccentricity of the curve equals 1, because these distances, for any point on the parabola, the distance to the focus is equal to the distance between, distance to the directrix. This means that the eccentricity of the curve equals 1. And in fact, whenever we have a parabola, this must be true. The eccentricity equals 1. Again, there are multiple ways of defining eccentricity and multiple ways of viewing parabolas, and it's actually quite interesting. And of course, they're a special case of the conic section, which is a very important, very interesting concept, speaking historically at least. But this function has obviously more properties than just that. Algebraically speaking, this function has two complex solutions. So if we have y equals x squared minus 1, and we're looking for the roots, or the zeros, we get x equals negative 1 and positive 1. Obviously, those are the solutions, and we can even consider factoring this polynomial into the linear factors, which would be, of course, x plus 1 and x minus 1. This might all seem basic, but in fact, this is an instance of roots of unity. It's a particular case where we get roots of unity. Because if you think about it, we're getting x squared equals 1, and we are taking, in some sense, we're solving this equation, so we're getting just a simple square root of unity. And of course we include the positive and negative values for that. But there are, in fact, more complicated cases of this, and I recommend you see this video over here to see my video on roots of unity, which describes it in more depth. And it actually uses the example of a 12th root of unity. So I hope you head over there and see that. But by any rate, let's move on to some more complicated things, shall we? If we use this equation, x squared minus 1, as an iterated function, we actually get a very profound result. An iterated function, in effect, means that we're using the last output as our next input for the function. So let me be clear, this is very different from taking a look at the ordinary graph of the function. Instead, we are repeatedly substituting and resubstituting values into the function and seeing what patterns emerge. So what we could end up with this iterated function, a single value to which the iterated function converges or gets, it gets closer, approaches after several iterations. Or in other words, usually we call it a fixed point, assuming that there is a fixed point, assuming that there is a single rational value for which, when we substitute it into the equation of the iterated function, we get that value again, repeated. So that's one thing we could get. We could also get a periodic orbit, It's a second possibility. So we could have a0, a1, a2, a3, for example, and then when we substitute a3 into the function, we get a0. And then it keeps going. a1, a2, a3, and it repeats again, a0. And so that's sort of this is actually the case of a periodic orbit. You would have period equal to 4 in this particular case, because it takes 4 iterations to get back to the start. Or we could actually, after several iterations, we could in fact get a divergent result, or something that we say escapes to infinity. So something that doesn't converge to any, regular pattern. It just goes off to infinity, gets larger and larger, and we'll see some examples of these. But I'm just trying to give some general information here. So to find, for instance, fixed points algebraically, we would need to set x equal to f of x for some predefined function, and then we would solve the polynomial that arises, algebraically. And the reason this works is that what we're really saying is that for the sequence that arises, we want a of n plus 1 to equal f of a of n, or a sub n. So we actually know that this is the general rule that works for any iterated function. We want the next sequence to equal f of the last output, right? It's based on the definition of an iterated function. And in this particular case, we're setting x equal to f of x for some value of x, to be solved for, in other words, in order to figure out, well, what is the value, if there is one, for which the output is the same as the input of the iterated function. So what exactly is the value of the fixed point? And so an example of this, let's say we had the function f of x equals square root of x. So if we study the square root function as an iterated function, we do end up with a couple of fixed points. And so what are they is a natural question, right? So we would say x equals the square root of x. From here we can square both sides, so x squared equals just x. And then after that we can say x squared minus x equals 0. And this is relatively easy to factor. Of course, you could use the quadratic formula, but it's simpler to factor. We can simply say x times quantity x minus 1 equals 0, and we end up with these two solutions, which are of course 0 and 1. This might seem like a digression, but we're going to get back to our main function soon, I promise you. So this is a particular case where we have the square root of x, and I'd like to show you as an example how we can compute this with a calculator and verify that 1 is a valid, just as an example, that 1 is a valid fixed point for this iterated function. So with a calculator, if we were to just say, just starting with 0.5, for instance, as an arbitrary starting value, and then if we were to say, well, let's take the square root of that, so what is the square root of x? Okay, something like 0.7071, that's actually equal to about root 2 over 2. But basically, what we can do is repeatedly take the square root of our answer. So, again, assuming that f of x equals the square root of x, as I just defined it right here, we're taking the square root of the last output. So this is one output. Let's take the square root of that. That's our next output. Take the square root of that, and, that's why it's called an iterated function. We just keep repeating this process. And sure enough, after several iterations, we end up with 1 as our, as sort of our fixed point. And from there, if we were to take the square root again, we just get 1. So that's why it is a fixed point, by definition. But we also see, experimentally, that's what we get. Now, you might ask, well, what happens when we use a different starting value? Well, that's a good question. If we were to use 0.25 or something like that. Let's try it. Square root of x. And then square root of that answer. Well, in this case, we do end up back at 1, indeed. So it is certainly a valid fixed point, with, even with slightly variable, starting values. Although it's a very interesting point I'd like to make, that with different starting values, you can easily end up in different places. and it's sort of related to chaos theory, and it's actually related to the butterfly effect, where if we change this initial value ever just very, very slightly, we can get completely different results. So we might not even end up with one. We might diverge to infinity, or we might get to some other cycle, or we might, there are different possibilities, is what I like to emphasize. But this is just all this detail about iterated functions. So now I'm just trying it with, I think, 0.05 is the starting, or the initial value. And if you keep square rooting that, indeed we get 1 in the end, yeah, as a fixed point. So square root of x is actually a relatively stable function compared to some others. But I'm glad, I'm glad you're able to see that. I hope you hope that made sense. Obviously, let me know if you have any questions. But I just wanted to show you that. Another thing you might like is if we chose a more complicated function. How about we tried, well, you know what? I'm gonna set this value equal to maybe 0.70. Oh, sorry, 0.70. That's what x will start as. That's our initial condition. Value. And let's say we use the function 0.5 x squared plus 0.5. So we end up with 0.745 right now. But let's say we, again, repeat this function, so make it an iterated function, and just keep using, the answer, or the last output, as our new input. So just keep doing that after a long amount of time. And in fact, this takes quite a long time to converge. You can see right now how slowly it converges. But as we're waiting, let me just keep talking. It appears that many papers about iterated functions, and especially the related IFS, something called an iterated function system, which are used to create fractals. Many papers about these topics were written in the 1980s onward. And I suppose I'll put more links in the description about this. I think it's fairly interesting, but hopefully you're seeing about now that we are, eventually this function is actually converging upon 1. It's getting closer and closer. I hope that's clear. And we can, of course, we could, if we wanted to, prove algebraically, or at least demonstrate algebraically, that this must be true with the given function. So, again, I used 1/2 x squared plus 1/2 is our function. So that's going to be our new function, f of x. And let's say we wanted to find, again, the fixed points for this iterated function, if it has any. And in this case, of course, it does. X equals f of x. So we set them equal, and then solve for that particular value of x, for which this statement is true. So at that point, what we can say is 2x equals x squared plus 1, x squared minus 2x plus 1 equals 0, and of course, that is a perfect square trinomial, and we indeed get x equals 1 as our one and only fixed point of this equation, or of this iterated function. So, thank you for watching. Actually, we're not quite finished yet, because I think we're forgetting something. The main function in this video. So, if we use this function, x squared minus 1, let me show you what happens. If we have x squared minus 1 as our iterated function, and we're finding the fixed points, so x is equal to that, that polynomial, and we're solving for the value of x, well, what do we get? We get x squared minus x minus 1 equals 0. Now, this is actually a pretty famous polynomial in mathematics, in that its solutions, if you use the quadratic formula, end up as 1 plus or minus the square root of 5 all over 2. Now, this might not look familiar, or it might, because it turns out that this positive solution is phi, the golden ratio. Approximately 1.6180339. And the negative solution is also closely related to phi. In fact, it is equal to 1 minus phi. So let me just make a note of that. It gives rise to phi, which is 1 plus the square root of 5 all over 2, about 1.618. I hope you can read that. 0.339, and of course it is an irrational constant. And we also get, as another solution, 1 minus phi. So about negative 0.618, 0.339, etc.